Hi folks, Mr. Ackerman here. Thanks for watching. We're starting a new unit. The topic of the unit is called kinematics, and it's the study of motion, although from the point of view of some of the variables like speed, distance, and time, we're going to be talking about the results of motion, the things that you can easily observe, like where an object is or how fast it's moving or how long it takes to get somewhere. Although, interestingly, we're not going to do it by talking about why the things are moving the way they're moving. That's for another unit where we talk about something called forces. But for now, let's get started. In response to some of your feedback, I'm going to try to make videos shorter, and one way I'm going to do that is by, instead of talking over this first frame like I normally do, I'm going to ask you to pause your video, take a look at the questions we're going to answer today, the schedule, the related topics in the schedule, and also the learning goals and success criteria. So pause your video now and have a look at those. Okay, and you're back. I hope you've had a chance. And so now we've saved a few minutes. We're going to get right into the new topic. The topic is speed, distance, and time. So to get us started, I want you to think of a moving object. When an object like a car, for example, moves, it obviously covers a certain amount of distance in a certain amount of time. For example, you can measure out with a meter stick how far the car goes, and you could use a stopwatch to measure how long it takes, and that usually gives us an idea of what we call speed. So before we can talk about all this, we've got to talk about the units that we're using to make measurements. And of course, when we're talking about distance, we usually use meters as our standard unit of measurement. Of course, we don't have to use just meters. We can also use kilometers, or we could use centimeters. In some cases, we use really large units that astronomers use called light years. If you're interested in astronomy, you might want to look into what those are. We might even use tiny units like millimeters or micrometers or even nanometers. Whatever the case may be, they always boil down to some multiple of meters. And so you got to get used to that. Of course, you all know what a meter looks like. Just think of a meter stick. Now, the object is going to be moving and cover a certain distance in a certain amount of time. What time units do we use to discuss the movement of an object? Of course, that would be seconds as our standard. The symbol is S. However, it doesn't mean we have to use symbols. You may also see us using hours, or we could be using minutes. We could be using years, which, by the way, in our system of measurement would be the letter A. That's A for annum, or annual, if you've heard that word before. We could use other units as well, but these are kind of standard units, although the basic one is seconds. So when we're talking about speed, now you know from the last unit that speed equals distance over time, and today we're going to learn a slight variation on that formula. However, since we're dividing distance, which is often in meters, by time, which is often in seconds, of course, we're going to get some answer in meters per second. However, another very common unit of measurement for speed involves what you see if you get into a car, kilometers and hours. And so what I'd like to do right now is just pause for a moment and ask you, what is the relationship between kilometers per hour and meters per second? How do you convert from one to the other? Well, to take an example, let's actually do something. Let's do an example that we might be able to relate to. Suppose you're in your car and you look down at the speedometer and it says 100 kilometers per hour. And suppose I ask you, what is that in meters per second? So the question might say, convert to meters per second. How would you go about doing this? Well, it's actually not that hard. The first thing to realize is that a kilometer is equal to 1,000 meters. And you guys know your metric prefixes, so you know kilo means 1,000 meters. What about hours? You'd have to convert hours into seconds. Now think about it for a minute. There are 60 minutes in an hour. And of course, there are 60, where am I here? There's 60 minutes in an hour, and there are 60 seconds in a minute. There we go, a little brain freeze for you there. Even teachers get that sometimes. Minutes cancel out. and now we get down to 60 times 60 is 3,600 seconds per hour. So that means I can replace hours here in seconds with the number 3,600. Okay, so basically to get to meters per second, I'm going to have the original 100 kilometers per hour times 3,600, sorry, 1 second there, I'm getting well ahead of myself, times 1,000 meters in a kilometer. And now we have to divide, because this is in the denominator, so we're dividing by, let me just move this out of the way for a sec, by 3,600 seconds in an hour, and that should get us the right answer. Let's see how that's going to work. Remember, when you divide a fraction, you're supposed to flip the fraction and multiply. So that's 100 kilometers per hour times 1,000 meters per kilometer, and that'll be times 1 over 3,600. This is because we're dividing, and that'll be hours per second. And now look what happens to all of our units. Hours cancels with hours, kilometers cancels with kilometers, and we are left with 100 times 1,000 over 3,600, and that's going to leave us with meters per second. And what does this number come out to? I should be putting equal signs in here as I go. If you run this through your calculator, you're going to get 1,000 times 1,000 divided by 3,600. I hope you're doing this with me. And, whoops, I realize I put in an extra 0 there. Didn't mean to do that. There we go. What you're going to get is 27.7 repeating meters per second. So notice that when you go from kilometers per hour to meters per second, the number becomes less. How much less? Well, let's do a simple ratio here. 100 divided by 27.7 repeating, what's that give you? Well, if you run this through your calculator, maybe you'll be surprised, or maybe you won't be surprised, to find that you get the number 3.6. Try that on your calculator now and see that you actually come out with 3.6. And this is actually what we call the conversion factor between kilometers per hour and meters per second. So if you ever have to convert from one to the other, remember the number 3.6 and you should be fine. For kilometers per hour into meters per second, what are you going to do? You're going to divide, because we end up with a smaller number than we started with. And if you're going the other way, you will multiply. You'll just do the reverse. Meters per second into kilometers per hour times 3.6. So this is a handy little thing to remember. You might want to copy this somewhere in your notes so that you don't forget. Okay, there's your conversion between the two common units, and that completes our initial discussion about distance, time, and speed, how they all go together. Now I'd like to try a little example with you here, and this one has a driver who's traveling a certain distance in a certain amount of time, and then an additional distance in a subsequent amount of time. So let's try to draw this out. You're going to notice that diagrams are extremely important in this unit because you have to try to visualize something moving. Best way to do that is with a picture. So the driver maybe starts here, and here is your car. Driver's moving along and travels 225 meters. So I'm going to write this out. Now when we're talking about distance, as you learned in the previous unit, the letter is D that we use. However, remember that Greek letter delta? We're also going to start using this one. So here's your first new symbol officially, delta D for the distance. And of course this takes 19 seconds, and as we learned in the last unit, the symbol for that is delta T. Now there's an additional 439 meters, so I'm going to write that over here, 439 meters, going all the way, let's say, to the end in a time of an additional 41 seconds. Now, got a little bit of confusion here. There's two delta Ds which are different, so let me call them delta D1 and delta D2, delta T1 and delta T2. Now that our diagram accurately represents what's going on, let's do part A. Compute her average speed during each time interval. So here's a new term for you that maybe we haven't discussed at this point, average speed. When we talk about average speed, we mean the same thing you talk about when you do any average. What we're trying to do is just average out over all of the time the total distance. We don't know exactly what speed she was going at any moment in these 19 seconds. However, on average, 225 meters in 19 seconds. So that's going to be V for speed equals delta D over delta T, 225 meters in 19 seconds. And because this is an average speed, we put the little letters AV underneath the V. So this is called a subscript when you write the letters just below the main letter. VAV, and this means average speed. And average speed is actually just all the distance you covered in all the time. For the first time interval, the first one over here, that's going to be this, which if I run that through my calculator, is going to be 225 divided by 19, and that gives me, I get 11.84 and a whole bunch of other digits meters per second. Now I can do the same thing over here. I can calculate the VAV, the average speed in here, where 439 meters were covered in 41 seconds. And what do I get here? So I go 439 divided by 41, and this time I get a slightly different number, 10.7, well, it rounds to 10.71 meters per second. Now once again, notice there's two intervals here, so it wouldn't be a bad idea to call this VAV1 and VAV2, delta D1 over delta T1, delta D2 over delta T2. If you're starting to notice that the symbols can get a little tricky here, you're absolutely right. It's going to be very important in this unit that you pay attention to symbols and you accurately record them. Otherwise, you might end up being even more confused than you need to be. So we've done part A now. We've found the average speed during each time interval, and that wasn't too hard. Part B might be a little bit tricky for some of you. Compute her average speed over both intervals. So what happens when we compute her average speed for the entire trip? Now think about this for a minute. Pause the video if you have to. How would you do that? Okay, now you're back. You've thought about how to compute the average. Now I know that when a lot of you think of averages, you think, well, just take the total number that you have. We've got two average speeds. We've got this one, and we've got this one. Why don't we just add those up? 11.84 plus 10.71 and divide by 2. That's what I always do when I average. I add the things up and I divide by the number that I've got. And if you do this, what number do you get? 11.84, I'm adding on my calculator right now, plus 10.71 equals, and I divide by 2, I get a number of 11.275 meters per second, which sounds good, but is it? Well, I'm going to put a question mark here, and the reason I'm going to do that is because I want you to think about what average speed really means. If average speed is distance over time, if we know that VAV equals distance divided by time, and if they're asking us to compute that over both intervals, let's see what would happen if we just add up both distances, 225 meters plus 439 meters, and we divide that by the time of 19 seconds plus the 41 seconds, then what would we get? So I'm going to add this up, 225 plus 439, that gives me 664 meters. And of course 19 and 41 seconds is 60 seconds. What do I get here? And you might be surprised, maybe you won't be, I don't know, to find that you get this number, which is close to the number we got here, but is close good enough? We're only off by a few tenths of a meter per second, but actually, as it turns out, this was incorrect. Why? I'll leave it to you to think about that for a moment. Pause the video and think about why this one is wrong. To help convince you that this one is wrong, let me first try to convince you that this one is right. This calculation used what we call the definition of average speed. Average speed is defined in physics as total distance over total time. Okay? So if we use the definition, we will always get to the correct answer. This over here is not the definition of average speed. This is what you might think of as the definition of average, adding up and dividing by however many things you've got. Can you figure out why this didn't work? Well, this one was the correct answer. Pause the video and think about it for a minute, and when you get back, I'll give you the answer. Okay, so you're back, and let's think. Why did this give the wrong answer? The reason is, if you actually look at the amount of time spent driving at this interval and the amount of time spent driving during this interval, they are not the same. Therefore, to add up both average speeds and divide them by 2 as if they are equally important is incorrect. When you do what you normally think of as an average, you get the wrong answer here because different amounts of time were spent at different speeds. However, when you use the definition of average speed, total distance over total time, you always get the right answer because that's what physics is all about. It's about definitions which you have to respect. And of course, the definitions include symbols. So you've got to be good at keeping track of those symbols. Okay? One final slide that I have for you is the difference between average speed and instantaneous speed. Well, very simply, we now know what average speed is. It's just total distance divided by total time. It doesn't really tell you what you were doing during the driving or the moving of that total distance. All it gives you is an overall idea. On the other hand, instantaneous speed, which is given the symbol VINST for instantaneous, you could think of as your speed at any given moment during the motion. Now, when would you, or how would you measure the instantaneous speed? Well, if you've ever driven a car, you look at the speedometer. If you're a police officer trying to determine if people are speeding, you might use a radar gun. But for the average speed, all we need to know is how far you went in how much time. And so I'll leave you with one interesting little thought experiment or an idea, something for you to ponder. Imagine this. Imagine that you're a police officer and you're trying to catch people who are speeding. There's two ways you can do it. You could use a radar gun, which will give you the instantaneous speed, the speed at any moment for the car. And that would involve you hiding out at the side of the road and pointing your radar gun at people. What if you tried to do the following? What if you sort of measured off a distance along the highway, a known distance? Let's say 100 meters, just for argument's sake. And let's say you and your partner stood at either ends of the 100 meters and used a walkie-talkie to communicate. And when the car passes your partner, you start the timer. And when the car gets to you, you stop the timer. So you know the time, and you know the distance, and you can compute what's called an average speed. What do you think about the police saying, okay, well, we computed your average speed, If that's over the speed limit, then we know you were speeding, we're going to give you a speeding ticket. Should they be allowed to do that? Or should they have to use a radar gun? Or does it even matter? What sort of different results would occur if the police used this distance, the averaging method, versus the instantaneous method, the radar gun method? Anyway, something for you to think about, and I will see you in class. Take care.